Hello all. Today we'll talk about radio frames. What are radio frames and what are the components of the radio frames and few other topics. So why this radio frame topic is important? In order to understand how actually the transmission of the data or transmission of the messages happens in the 5G subsystem, we need to understand the basic blocks of 5G, which is nothing but radio frames. So let's start. Intro to the 5G frame structures. So frames are divided into something called as subframes, which are further divided into slots and that are further divided into symbols. We'll cover in detail each of this and what it actually means. To understand 5G frames completely, we'll also cover topics of subcarriers, resource elements, and resource blocks. So let's start with our first topic, which is just a revision to the basics called as bandwidth. Now, what is bandwidth? Bandwidth in simple term is consecutive frequency or a set of consecutive frequency which has a lower and a upper bound defined. Or in other words, the difference between the lower and the higher frequency band. So let's say you have frequency X and frequency Y, and there are a lot of frequencies in between. The difference, that is X minus Y, is something called bandwidth. Let's understand with an example. Let's say you have a device and the device is capable of transmitting and receiving anything between 3.6 gigahertz to 3.5 gigahertz. So then by the definition your upper bandwidth is 3.6 and the lower bandwidth is 3.5. So the difference between them is called the bandwidth, which is zero point 0.1 gigahertz. And otherwise we can also say which is 100 megahertz. Let's take another example where a device is capable of transmitting and receiving between 700 megahertz to 650 megahertz. So here 700 megahertz is your upper bandwidth and 650 megahertz is your lower bandwidth. Then the difference between them is 50 megahertz, which is your bandwidth. Now, the combination of bandwidth and frequency together is called a spectrum. So we'll take an example to understand what is a spectrum with reference to understanding of bandwidth. So let's say you have a 70 megahertz spectrum starting from 3.5 gigahertz, which means that you can transmit and receive anything between range from 3.5 gigahertz to 3.57 gigahertz. The spectrum is something that operators buys and the operator has sole rights of radiating, that is transmitting or receiving anything within that range. So if you have, let's say, 100 megahertz of spectrum starting at 3.5, so that means 3.5 gigahertz. So that means you can radiate from 3.5 gigahertz to 3.6 gigahertz, and no other entity can use this spectrum which is allocated to you. Moving forward, let us understand the concept of numerology in terms of subcarrier spacing. To understand subcarrier spacing, let us first understand in simple term what is a subcarrier. A subcarrier is nothing but a frequency. That's a simple definition of a subcarrier. Now, there are more things into it, but for the understanding of the topic, we'll skip the minor details, as I said earlier, and we'll focus on the higher definition. Now, subcarrier spacing refers to distance between adjacent spacing or how frequencies or how adjacent frequencies are to each other. Or we can also say a set of frequency, consecutive frequency, how tightly or loosely they are packed. Let's understand with the example. But before starting in general, let's understand one thing. In context of 5G, everything is in terms of 12 subcarriers. Now, why there are 12 subcarriers? We won't go into detail, but this is something called a standard. So whenever you reference to a subcarrier spacing in 5G, it will be always in respect of 12 subcarrier. So for example, if you have 12 subcarrier, each subcarrier are 180 kilohertz apart. Then with reference to 5G subsystem, this is known as subcarrier spacing of 15 kilohertz. Similarly, 12 subcarrier, each subcarrier 360 kilohertz apart is termed as 30 kilohertz subcarrier spacing. Now this each 15 and 30 kilohertz is nothing but they represent the numerology. So let's further understand with an example. So let's say you have a pattern like this. These are 12 subcarriers, and you have another pattern. Again, these are 12 subcarriers. As you can see here, subcarriers are tightly packed compared to this. So for reference or for sake of arguments, if we assume that this is 15 kilohertz, this means that each of these frequencies are 180 kilohertz apart. Similarly, in context of this, if we assume it as 30 kilohertz, then each will be 360-degree apart. As I said, significance of SC ability is define how to really loosely or tightly packed things are. Now here I am referring it as things and not any particular uh, technical word because it's not just the difference between the subcarriers, but it also has more information to it that will cover up. Now, 3GPP, which is a standardization body, has defined the following numerologies. Accordingly, the following subcarrier spacing. So, numerology 0 refers to 15 kilohertz of subcarrier spacing. Numerology 1 refers to 30 kilohertz, 2 as 60, 3 as 120, 4 as 240, and 5 as 480 kilohertz. Mm. For the context of understanding, in upcoming slides, we'll only talk about numerology 0 and 1. And then the same concept can be extended to other numerologies as well. Moving forward, now let us understand the concept of radio frames and subframes. The radio frames are the largest entity in 5G reference. So they in terms of having a reference or in terms of having an uh, technical point, the largest entity is radio frames, which are further divided into subframes. As I said, subframes which are further divided into slots which are further divided into symbols. The length or the duration of the radio frame is always constant, which is 10 milliseconds. So whatever numerology you use or whatever the mode of transmission in 5G NR is, the radio frame have a fixed length of 10 milliseconds. Now, Based on this fixed length, the length of the other components, and based on numerology, mm, length of the other components is calculated. How this other component calculation will happen, we'll study one by one. So now each radio frame consists of 10 subframes, and each subframe is of 1 millisecond duration. So if you have 10 millisecond as radio frame duration, and if you have 10 subframe, then 10 millisecond by 10 subframe, which will give you one subframe time, is 1 millisecond. So for a visualization, this is what a 10 millisecond radio frame will be looking like. And then we have 10 subframe starting from subframe 0 to subframe 1, 2, and so on to subframe 9, each of 1 millisecond. Now let's move forward and understand the concept of slots. As we know, each subframe is divided into slots. The number of slots in each subframe and the length and time of the slots varies as per numerology. So there are two things here. How many slots are there in a subframe is a function of numerology, and the duration of that slot or length of that slot with respect to time is also depending on the numerology. Let us understand further. So as we can see, if you have numerology 1, the number of slots will be 1, and so the slot length will be 1 millisecond. Further, if you have numerology 1, the number of slots will be 2, with each slot of 0.5 milliseconds, and so on and so forth. Let us understand with the representation. So as you can see, we have a radio frame of 10 milliseconds, which is divided into 10 subframes, each of 1 millisecond. Now here we have taken numerology 0 in 15 kilohertz and numerology 1, which is 30 kilohertz, as a reference. As we know in this table, numerology 0 have only one slot, which is a 1 millisecond. So here also we have one slot, and the duration of the slot is 1 millisecond. We can further see that in numerology 1, we have two slots, each of 0.5 milliseconds. So we can see here is slot 0 and slot 1, which is of 0.5 millisecond. So if you are having subcarriers seeing as 30 kilohertz, basically numerology 1, so this subframe will contain these two slots. But if you have only one numerology, then one subframe, I mean numerology 0, then this subframe will only contain one slot of 1 millisecond. Similarly, if you have numerology 2, so your subframe will have 4 slots. As we know, subframe is of 1 millisecond, so the length of 4 slots will be 1 by 4, which is nothing but 0.5 milliseconds. Similarly, if you have numerology 3, 8 slots, length of each slot will be 1 by 8, and for numerology 4 it will be 1 by 16, and for numerology 5 it will be 1 by 32, which is nothing but 0.03125 milliseconds. Now let's come to symbols. Each slot is further divided into symbols. The number of symbols are 14, which is a fixed regardless of numerology. So if you have numerology 0, 1, 2, 3, 4, or 5, you will always have 14 symbols. The varying factor here is the length or the time duration of the symbol. This is supposed to be symbol, which varies with numerology. Again, let us understand with an example. So if you have numerology 0, and we know numerology 0, you have only one slot, and each slot will have 14 symbols. So the duration of each symbol will be 1 by 14. Similarly, for numerology 1, you have two slots. Now the slot, as we saw in the last session of the slot length will be zero point 0.5, hence the symbol will be zero point 0.5 by 14 milliseconds. So on and so forth. For numerology 4, it will be 0.625 by 14 milliseconds. Now let us visualize the symbols. So here we have taken example of again numerology 0 and numerology 1. So here you can see 1 millisecond, and for numerology 0 we can see 0 to this will be 13. So this is 0 to 13, 14 symbols. Similarly, now for numerology 1, in one subframe you have two slots, and each slots will have 14 symbols. So this is how a structure will look like. So you have, try to visualize it better. So we have one radio frame. Let me draw it here. We have a radio frame which is of 1 millisecond. Now this radio frame is divided into equal subframes, approximately 10 equal subframes, 0 to 9, each of 1 millisecond. Now one subframe, based on numerology, either it can have one slot if it is numerology 0, which is represented by mu, which is 15 kilohertz, and the duration of the slot will be also 1 millisecond. Further, this slot will be divided into equal smaller chunks on a symbol starting from 0, 13, each of length 1 by 14 milliseconds. With a numerology 2, this representation will be something like this: radio frame, then subframe, then slot. Since its numerology is 1, 30 kilohertz. So we'll have two slots, 0 and 1, each of 0.5 milliseconds. Now each of this will have 13 symbols, sorry 14 symbols, 0 to 13, of length 0.5 by 14. Now if you want to take it to numerology 2, 60 kilohertz, then we'll start from slot level. One subframe is a 1 millisecond, and so we have 4 slots, 1 by 4. This is 1 by 4 milliseconds, 1 by 4 milliseconds, by 4. This is nothing but 0.25 milliseconds. Now each of this has 0 to 13, 0 to 13, 0 to 13, and 0 to 13 symbols. Here the duration of the F symbol will be 0.25 by 14. I hope till here we are clear about how the division works. But eventually you need to able to carry a data. Uh, the representation of data in the digital term is nothing but a bit or a set of bits. So how you do that? Do symbol carry that particular information or do symbol have bits? No, symbols are just a location in time domain. Now we know there are 12 subcarriers and we know there are 14 symbols. Now if we combine those two, there is some we come to the concept of resource elements. So let us understand resource elements. Resource elements is a smallest unit in 5G inner which can be transmitted. It's a fundamental unit like uh, like an atom, or we can say to be more precise, yeah, you can understand it as an atom. Now, as I told, resource element is one which carries actual data. So resource elements is where the bits are. Now, in simple term, a resource element is made up of one subcarrier in frequency domain and one symbol in time domain. This will be time. Now let's understand with the example. As you can see in the diagram, we have symbol 0, symbol 1, and so on and so forth till symbol 13, 14 symbol, and I have subcarriers, nothing but my frequencies, 12 subcarrier. Uh, so my x-axis is time and my y-axis is frequency. So based on the numerology, as I saw, the definition of this will be, so this is again 1 by 14 starting, then we'll add more 1 by 14, 1 by 14, so on and so forth. So assume that this is 0, this is where your 1 millisecond boundary ends, which each having 1 by 14 as a time reference. Now as per definition, it is one subcarrier in frequency domain and one symbol in time domain. So this is RE, this is a RE, this is a RE, this is a RE, this is a RE. All the individual elements or all the individual blocks in this matrices are nothing but a resource element. So overall, if you want to know how many resource elements are in graph, it's nothing but 14 cross 12. This many resource element we have in the particular grid. And in this resource element, you will have your bits X, bit Y, bit Z. Each of these will carry bits. How many bits they carry or what kind of information carry will come up in further session. Let's move on to another interesting topic called resource block. Resource block is nothing but a combination of resource element, and that precise combination is 12 symbols in frequency domain and one symbol in time domain is defined as a resource block. But those 12 consecutive, it has to be 12 consecutive resource element. I will further repeat, 12 consecutive resource element, which is nothing but 12 frequency domains and one time domain. Let us let us understand with a visualization. So here is again same example. Here we contain on the x-axis we have 14 symbols and on y-axis we have 12 subcarrier. Now resource block is nothing but you can say this 12 subcarrier in frequency domain and one symbol in time domain is a resource block. Similarly, this is a resource block, this is a resource block, like and so forth. This is a resource block. So overall, in the current grid or in the current matrix, we can see that there are total 14 resource blocks as there are total number of 14 symbols. Now, how many resource blocks are there in a 5G subsystem? Let's understand. So the number of resource blocks depends upon the bandwidth. Let's understand with an example. Let's take a bandwidth of 30 megahertz. As we know, each resource block consists of 12 subcarriers. Now the number of resource blocks depends on numerology. We'll understand again further with an example. So let's have bandwidth of 30 megahertz. We know there are 12 subcarriers. Let us take the numerology is 0. Then we know the numerology means 0 means 15 kilohertz of subcarrier spacing. So now let us find out the number of subcarriers. That is 30 megahertz divided by 15 kilohertz, which is nothing but 2000 subcarriers. Now, as we know, the definition of resource block is 12 subcarriers in frequency domain and one symbol in time domain. So the number of RBs will be 2000 by 12, which is 166. If we take example of numerology 1, which is nothing but 30 kilohertz of subcarrier spacing. So let us find out the number of subcarrier, which is 1000. So the number of RBs will be here it will be 1000 by 12, which is equal to 83. But this is approximately equal to 162 or 163, and this is around 78. It is less than the calculated number. This is because there is something called guard bands or reference signal which take up some of the carriers. So the exact number of RBs varies as per the uh, numerology, and there will be some adjustments of the guard band. Now let us take a whole visualization of things. Now here, for the sake of simplicity, I'm taking numerology as 1, which is 30 kilohertz of flux spacing. So at the beginning, I got a radio frame that has to be transmitted. So when I say radio frame has to be transmitted, we'll go to individual level. It is the symbol, sorry, this is a frame which is transmitted. Now when I further say subframe to be transmitted, it is nothing but a slot to be transmitted. Millisecond, 1 millisecond, 1.5 millisecond, 1.5 millisecond. Now when I say uh, slot has to be transmitted, it further means symbols has to be transmitted. Here we know from the PS example that there is 0 to 13, total 14 symbols. Similarly, 0 to 13, total 14 symbols. But what actually happens as we saw resource grid? So now you let us define this box as a resource block, which is nothing but 12 subcarriers and 14 symbols 0 to 13, 1 to 12. Let us name this as resource block 1. And as we know, with the example of 30 kilohertz, we can find number of subcarrier. So with respect to 100 megahertz, and as we know, it is numerology one, which is 30 kilohertz. You will get something around 3333 subcarrier, which if I divide by 12 and adjusting for the guard band, it will be 273 radio blocks, RBs. So if this is RB1 and if this is RB2, so in a 100 megawatt bandwidth, we'll have RB1, RB2 all the way to RB 273 being transmitted in one slot. This is nothing but totally 3333 subcarriers transmitted considering 100 megahertz bandwidth with 30 kilohertz subcarrier spacing. Now this again repeats one more time, and this too completes only one slot, but in a subframe we have two slots, so it is nothing but 273 into 2, which is been transmitted into one subframe. Now we know there are 10 subframes in a radio frame, so total it will be 273 into 2 into 10 resource blocks being transmitted in one radio frame. So this explains the scale of the 5G, which is really big. In next session, we'll cover how bits are being transmitted as a part of a resource element and as a part of a resource block. Thank you.